Okay, we open this chapter with a discussion about concavity and points of inflection. And like a lot of math lessons, this title isn't very meaningful until partway through the lesson. So let's leave it exactly what those things mean for the lesson. So this is the final tool we need for accurately graphing functions. The concept we are going to consider is called concavity. Essentially, concavity is the curvature of the function. So not too complicated here, just which way things are curving. So basically you want to know which way this thing bends. So let's look at a simple one. And actually, it's a simple situation, but there's a lot going on here about slopes. So if you look at this function here, and it's just a simple function that goes up for a while, down for a while, and then back up for a while. And I want to first focus on these words at the bottom here, concave down and concave up, because that really gets the whole idea of concavity clear. And there's a whole bunch of numbers on the graph. Don't worry about those for a second. And really focus on the blue part of the graph, where it says the blue writing there. This left side of the graph here is all concave down, which just simply means it's bending downwards. Way back when we first studied parabolas, we would have called this opening downwards. Now, on the other side, it's concave up, which means it's bending up. And there's a ton to talk about. But for now, let's just talk about the other situations and I'm going to come back to all those numbers there. So all those numbers are going to be really important to what we're talking about. But for now, just some other illustrations. It doesn't have to go bend all the way down or bend all the way up to be concave up or down. So you can see there's some partial parts here. This is concave down, even though we've only got one half of the curve, and this is concave down, and this is concave up, and this is concave up. But notice there's something more to these sections here, is that first one was concave down, but the function was going up. Then we've got concave down where the function's going down. And hopefully you're sort of thinking about the first derivative here, in that this first section here is a section where the first derivative would be greater than 0, and here's a spot where the first derivative would be less than 0, because we're going from going up to going down. And over here, we've got f prime less than 0, because it's going down, and then here, f prime would be greater than 0 because this function is going up again. So we can talk about the derivative, but there's something else going on here in each of these sections, is that the two graphs on the left are concave down, and the two on the right are concave up. So there's obviously more to talk about. So let's get back to these numbers here. I just want to talk about, and I'm going to go to a different color of highlighter here, like an orange highlighter here, so I can talk about one section of the graph. I want to talk about this section of the graph. In this section of the graph, let's talk about what the slopes are doing. It starts with a slope of 10 and then starts dropping. And they don't give you every single slope here, but this slope goes from like 10 to 4 to 0 to -3. And what's happening? The slopes are getting smaller. They're getting less and less positive as we get along there, and it goes all the way to 0 and down to -3. Now, when we're concave up, and I'm going to highlight that graph in green, that part of the graph there, the slopes start at -5, then they go -4, 0, 4, 10. See, they're coming back up again. Well, that's actually the whole story on concavity. When the slopes are getting smaller, we have concave down. When the slopes are getting bigger, we have concave up. That's simple and that complicated and all at the same time. So the key idea, let me just highlight that in the great red highlighter. Red highlighter means, whoa, this is important. That doesn't mean difficult. It just means important. This is the big moment of the lesson. When the slope is decreasing, the graph is concave down. When the slope is increasing, the graph is concave up. So we're talking about how the slope is changing. When we use the first derivative, we were talking about how is the graph changing. Now we want to know how is the slope changing. Well, how can we analyze when a slope is increasing or decreasing? And the answer is the second derivative. And I'm going to treat myself with some more red highlighting here. That's a very important phrase in all this. Again, I don't suggest that that's that difficult, but it's very, very important. So this is exactly what the second derivative measures. It measures how the first derivative, or how the slope, is changing. It's the rate of change of slope. So here's our test for concavity. This simple and this complicated all in one. I say simple because it's a fairly simple idea, but if you think about it for a second, it might be a little difficult to do. Not to think about, but to actually do this. But we'll get more idea of that in the next few lessons. So let f at x be differentiable. That means we can take the derivatives, and whose second derivative exists on an open interval, which means the second derivative isn't undefined or something like that. We won't run into too many of those situations, but we got to put it down there to say, well, we got to be able to take the derivative here. So the graph of the function is concave up if the double derivative is greater than 0. And I'm going to draw a little picture here. Switch over to a little pen here and say, hey, when we're concave up, we look like this. And when we're concave down, we look like this. I mean, we can be part of the graph like that, or part of the graph like that, but you're going to be concave down when the double derivative is less than 0. What if, ooh, some stuff missing there. Let me just fix that, tidy that up again. What if the double derivative equals 0? And when it equals 0, that means we've switched from concave up to concave down. And here it is right here. Let me draw an arrow to the point. We get what's called a point of inflection. New word there. A point of inflection is when you switch from concave up to concave down. Either way, if you go from concave up to concave down, it's a point of inflection, but also if you go from concave down to concave up. So, for any function, a point where the concavity changes is a point of inflection. Now, what does concavity tell us about the tangent appearing above or below the function's graph? If we draw a tangent anywhere, and I'll just draw a quick tangent in the concave down area of this graph here, can you see that the function will be less than the tangent? It will always be below the tangent. And when we're concave up, can you see that the function would always be above the tangent line when you're in that section? Very close. You know, if the concavity changes, then of course, farther away, it can come back and go, the graph can go below that particular tangent again. But nearby a tangent, you're going to be below when you're concave down, and you're going to be above when you're concave up. I mean, that matches with what we know about slopes. When it's concave down, if the slopes are getting smaller, of course, it's going to curve down away from the tangent. Okay. Oh, some more stuff here missing. Determine, here it says where f at x equal to x cubed plus 5x minus 2 is what we want here, is concave up and concave down. So what we've learned is that what we want here is the double derivative here. So let me go after the single derivative, f prime at x, single derivative here, let's see, 3x squared plus 5. And then so we want to analyze the double derivative here, which is f double prime at x is 6x. Pretty simple double derivative here, just to get the idea of what's going on here. So to be able to find out where it's concave up, we first want to find any points of inflection. So for points of inflection, set f double prime equal to 0. So I get 6x equal to 0. Pretty easy little solve there. So I've got x equals 0 as a potential point of inflection. This may remind you of the single derivative test. With single derivative, we go f prime equals 0, and then take those x values and build a single derivative chart to find out when it's increasing and decreasing. So now, instead, we build a second derivative chart. Great stuff here. We're going to now use the second derivative. So we want to look when x is less than 0, because that's the x value we found. That's the potential point of inflection. I say potential because, again, we found out with single derivatives that sometimes, even though it really looks like we're going to find a max or min in those situations, then we find out, oh, it wasn't actually a max or min. It was just where the derivative of 0. And here we may find that as well. But for now, let's just assume, moving forward, that most times, once we've found where it's equal to 0, that's where we're going to find this point of inflection. So now I've got my f double prime, which is 6x, and I want to analyze what's happening. And just like a single derivative chart, you're going to sort of test this thing out before 0 and after 0. And to go through the whole procedure here, let me just switch to another color here and choose some test values. I'm going to use a test value of, say, -2. And maybe +2, but you can choose anything you want over there. It doesn't have to be -2 and +2, anything that's less than 0. And you might remember, you might have all sorts of factors that you've got to work this through and figure this out. A simple one to start off with here, though. So we'd get a negative double derivative here, and we get a positive double derivative here. And so what that means is when we get a negative double derivative, that means we're concave down. And when we get a positive derivative, that means we're concave up, I'm going to just draw a little picture there. So we're just going to be sort of like that in that section there. So, but what does it say? Determine where the function is concave up and concave down. So concave down, x less than 0. Concave up, x greater than 0. So I've answered that question. Identify any points of inflection. So I've got a point of inflection at 0 comma, what's the value here? I got to put the 0 back into this function here. I can do that without too much work here, but lots of times you're gonna have to write down some stuff to figure out where it is. But subbing in 0 into this thing, I get my point of inflection at 0 comma negative 2. Okay, this is very helpful, and it's the last piece of the puzzle for graphing. You can imagine what we're going to do next is put this together with everything else we know about graphing. For now, though, that's enough for now, just to get the idea of concavity, and then we'll move on to some graphing examples in the next lesson or so. That's it for this lesson.